of crawling that I will introduce this morning. That is the peristaltic crawling. Peristaltic crawling is in a certain way similar in the sense that it is based again on friction and differential friction, but differently from the previous introduced kind of crawling. This system does not need, it does not require strictly anisotropic friction. Why? Let's consider this model here, where we have 3 modules which are not elongated, and 4 modules that are elongated. The modules which are not elongated act as anchoring segments, and then just the lengthening segment, the segment before the anchoring segment and the segment after, with respect to the head of the robot or of the animal that is to the left, to the right, just those 2 segments lengthening and shortening together. And what is the result of this shortening and elongation is that the body is pushed a little bit forward. You can draw yourself a whole collection of contraction waves that brings the body forward, and you can see another interesting part of peristaltic locomotion, that not the whole action is propulsive. So that one pushes the body forward, but then when we have the change of the anchor to bring the anchor back to the head of the body, you are not pushing forward your body, you are just changing the anchors. And if you go into the mathematics of that, again, using simple friction laws, you can see that for a body which length 1 and 1 minus n segments which are not elongated and n segments which are elongated at each time, you again want that the reactive force will be positive, and that leads you to the number of segments that can be moved each time. You can see that it is not required here that the figure on the formula on the bottom left, that it is not required the 2 friction coefficients are different. They can be even the same. You are only reducing the number of segments that you can use each time. Of course, if you have differential friction, you can move more segments. So again, it required an elongation and a contraction, let's say, that can be coupled, as most of the soft robots are doing right now, but no anisotropic friction is required. That's a very beautiful example of this kind of robot, which is actuated by only 1 actuator. So you can really distribute your let's say, you can exploit the structure of your agent to obtain a certain task with simple actuation. That's a common ground for all these kind of soft robots, for all crawling soft robots. And you can see that the robot is crawling. In the model, it's quite clear how, when the robot is in double anchoring phase, the body is not moving forward, they are just shifting the point. And then only when the real part is lifted, then you have a real shrinking or a real elongation of the body. So it's perfectly suited and perfectly drawn from true peristaltic actions and through friction forces. One pros of using soft components for this kind of crawling machine, we have also serpentine crawling that I didn't introduce that this morning, but is that you can use under actuation. So you can obtain locomotion with a few actuators, and you can distribute the forces along your whole body. Or you can work in harsh condition, and of course you can be resilient to damage, or you can adapt to the environment. Let's move then to the running and open locomotion. That's a video from BBC that is great. As always, they did amazing videos, but they are also, let's say, in a certain way, they are pushing forward our expectation for locomotive robots. But that they are too much. So let's see this goat. What it does. Look at how beautiful it is hopping and jumping on that rocks with incredibly dexterity. So that's the dream, of course, of people who work on legged robotics. But how much is this behavior controlled? So how much intelligence is the God putting inside this behavior, and how much it relies on other components? Of course, both questions are interesting, and both approach are extremely useful. But now we are looking into the mechanical part that can, and the compliant part that can aid you in obtaining these dexterities. This dexterity without increasing your control, your efforts on control. And most of the robots that try to replicate this kind of agile locomotion relies on what is called the spring-loaded inverted pendulum model. In this model, the whole leg is reduced to an elastic element. That means that while you in a flying phase, okay, the model is acting like in a ballistic way, so you have point mass model, and then when you touch the ground, that point here where you see the leg that is start touching the ground, the forces that are acting on the point mass model are based on the compression of the spring. So those are the relationships. They are quite simple. So you have the stiffness of your spring, that's the compression of the spring, and this is simply another way to indicate the sinus and the cosinus, the cosinus of the angle of attack. Okay. So by using the proper stiffness in combination, so the proper compliance, let's say, in combination with the mass, you can obtain self-stabilization of running. So that means that you guarantee stability with respect to disturbances by using the passive dynamics of your system. And that's a core example to build, and a core principle to build your robot in a way that when you're going to implement a more complex controller, then you have behind you some passive dynamics which helps you this kind of complex function. So we can put some components related to the mass to in this computer, but of course we can also put compliance on the body. What means compliance on the body? First of all, things that the organs that we have inside us are soft, but they are not sticky to our bodies. So they are moving inside our body, and that puzzles a lot biologists for a while, because they say, why are we wasting more energy to make our internal organs oscillate? But then some answer comes from peace and inertia, let's say, because what Roman did a lot of things to understand. It was easily to bring a load with elastically suspended loads instead of rigidly attached load. Why is that? Is that because when you have a locked load on your shoulder, then the load is moving with you in phase. But when you properly design the compliance of the suspended load, then you can obtain a counterphase movement of your load, and in such a way you are reducing the weight that you are carrying, and of course you are reducing the energy that your robot is putting inside your system. So that's unlocked example where you see that the backpack is not oscillating. Now let's see when the backpack is oscillating, so you are putting more energy on your system to move the backpack as well. Let's see both of them together, and you can see quite the difference. So the backpack is not oscillating, so you are not adding energy to the system. That can be easily modeled with a double mass coupled oscillator, and you can see that when you are below a certain stiffness suspension, then you are in counterphase. Otherwise, you are in phase, and so you are increasing the energy required to move your load, but of course also to carry a load with your legged robot. That reduce the energy consumption here. You can see about 10%. It's not so much, but in the long run, if you want to be a machine that really can help us a lot on kind of dangerous tasks for a long time, then it will be paramount. Now we talk about compliance on legs, compliance on body. I will go very briefly on shape-changing body that extend this concept of using not only compliance on leg but compliance on body with the form of body. And as an example, but this is just an example, I'm using underwater legged locomotion. Why is that? Because underwater forces are strictly related to the shape of the body itself. So what we discovered is that by properly designing the shape of the body, we can increase a lot the number of convergent states. So the number of states that have these self-stabilizing properties with respect to disturbances. You can see here the robot that is hopping by properly designing the shape of the wood, and in this case is fixed, and it is able to work over different substrates, even if it is subject to different kinds of disturbances. But of course, our last, let's say, our aim is to move toward a body that can change its shape, and in this way, we can really manage to move over different uneven terrains with different loads, and by only changing the shape of our body and letting the system behave in this kind of passive dynamics that help us. Very briefly, the last example, that is the jet propulsion of swimming. You can see here the octopus that is performing this jet propulsion locomotion, and here is a salt. Different ways, but the same mechanism is basically a variation of the linear momentum of the water that you are injecting in and you're ejecting them. Jellyfish use that, cephalopods use that, but what is interesting for soft robotics is that lot forces, again, are shape dependent. So when you have this kind of jet propulsion implemented with a soft propeller, basically when you are ejecting your water, you are reducing your frontal area. And in this way, you are reducing the dissipative force that you have on your body, and so you obtain additional thrust. As well, there is another force that is dependent, it's not a force, but it is a mass that is dependent on the shape of your body. So when you vary the shape of your body, you also reduce the added mass contribution that eventually lead to additional thrust as well. Of course, those are a lot of, let's say, not realistic implementation, but we also tested them in challenges that included people from all the world, basically, on semi-realistic scenario, so mock-up scenario which implemented some kind of realistic disaster environment, and all these robot challenges in this kind of locomotion competition. I will just highlight this locomotion competition and then we'll conclude my talk. It's just a cool video with different robots. Not all the locomotion that were employed in these challenges and here in this video were presented this morning. Just there's a few of them. A few of them, if you see toward more soft robots, you can see the tasks that are demanding. This is a wheel one with origami robot that was implementing two anchor crawling. You see that is completely soft. That's a kind of vibrational-based robot that can change the shape, and that's a legged, completely soft. It is not, let's say, it was a good example even if it is not completely successful. Okay, so that's more or less the end of my question. Of course, we have the new edition, if you are interested in, that will be held on April. And that's just to conclude, you can have the whole body that is soft, that usually enables your locomotion and rely more on the advantages that are related to adaptability and resilience. And on the other hand, you have only specific parts which are compliant and then enhance specific performances, for example, forces or stability of the locomotion. That's all. I hope that I'm in time, more or less. Maybe I'll just delay a little bit, but okay, it was nice, and thank you for your invitation, Fabio.
Thank you for coming, for accepting the invitation. I think this is a very interesting presentation about what has been done and the many opportunities that are in front of us and you as researchers. I think this is really one of the areas where you can do new stuff and discover new things, because as it is apparent also from this talk, many things that couldn't be done before can be done, and many problems are still there. So for a researcher, this is a very good situation. I think while Rory Green prepare for his presentation, we have time for a few questions. You may want to use the chat to book your question. Really, are you there? Yes. Okay, it's made great pleasure to present the next speaker, who is Ray Green from the University College London, who has done very, very cool work on architecture. And we actually talk about animating architecture. Ray, thanks for accepting the invitation, and the floor is yours. I'm afraid we still have some problem. You are there? So, can you hear me? No. Let's wait a few minutes while Ray is trying to connect. Really, I can see you, but I don't know if you are trying to say something.
Okay, let me try this. Let me see if this works better.
Now I can hear you.
Okay, I was trying to use the microphone on my headphones. Okay, so that's good. You can see me and you can hear me. The only thing I wanted to know was how to share slides with you. So how would I, where should I look for doing that? Oh, this is a strange system. I can't hear you now. Fabio, I'm afraid I can't hear you now, which is strange. I could hear you just up until a second ago. Hello? Unbelievable. Just working a moment. You can hear me okay? And for some reason, what a strange system. I can't hear anything. And my Italian's not that great for working with an interface that's in Italian at the moment. Choose second button, share screen, go to quick start. Let's see, how do I do my Italian? I use my Google Translate app. Share screen. So that says can now see content that you are sharing. Move onto upper or access controls to allow. I can't hear anybody, I'm afraid, at the moment. Can you hear me? Okay.
Sorry. You should see a dark, I see a dark screen.
Okay, great. But I can hear you now.
Good. That's good. Okay. Now you are sharing, I think, your screen, while you may share directly with,
yeah.
That's good. Now I see the presentation.
We there?
Yes,
We're good?
I see your presentation.
Amazing. Okay, gosh, I thought that was going to be quick.
No, as told, it's still a bit bumpy, so we do this, and we hope that the technology will improve over time, but there is still room for improvement. Okay, so it seems we are okay.
Yeah, so, great. And can you see my? Can you see the screen I'm looking at?
Yeah,
you can see the slide.
Yes, we can see it perfectly.
Is the chat bar that's in front of me also in your way, or is that actually hidden from you?
No.
Great. Okay, so that means that you've just got the slides. Okay, so if you can all hear me, I'll begin. Just give me a little okay, or off you go.
Both.
Okay. All right, great. Let's get going. All right, so hi everybody. I'm going to just talk a little bit about how I've been exploring robots for their aesthetic qualities primarily, and I'm going to just begin by saying a little bit about where I'm based. I'm based at University College London. We have a large facility dedicated to the use of robotics in architectural design. And a lot of what we do, and this is part of the research that I've done in the past, is looking at using industrial robots to do things like building molding elements to allow us to be able to pour concrete between molds and to actually be able to build prototypes and then actually to go on to build buildings. This is just a bit of video footage. I'm not sure what frame rate you'll be able to watch the footage at.
I'll see perfectly the video.
Fantastic. So this is just some of the molds that were cut. This is brought to site in central London. This is pouring of concrete, and it's pumped up a building and then poured into molds. Can you check your setting up of computer? Is that a message to me? We cannot hear very clear. Okay. Let me see if I can. If there's anything I can do. Let me see if there's something I can do about that. One second. Microphone. Let me see if this will help. Is this going to be? We cannot hear very clear. Is this? I've put the volumes right up now on these.
Now we lost him.
Can you hear me okay? Hello? Can you hear me?
Yes.
Okay, good.
We hear you. Yeah, we hear you. Yeah.
Okay, good. Just wanted to check. I got a message saying somebody couldn't hear me very clearly, so that's all. Okay, I'll carry on. Let me know if there's any problems. This is the result of that building that's just been completed in London. In some ways, this photograph shows you how, using very digital techniques, we've been able to actually create a building that's almost looks like it's glitchy. Something's got corrupted in the CAD model, but it actually also has bits of it that connect very closely to the existing vocabulary of the architecture that's around it. And so maybe you can change the internet connection, because I just got another message saying I have to maybe change my internet connection. Let me just see what happened there. It's not very stable. Okay, hold on. I'm going to try and see if I can improve that. Just 1 second. I've just done something to my network. I've just plugged in my.
We have noise in the background actually, so it's
just making sure everything else
bumpy the voice.
Okay.
No idea. Usually it's a bandwidth problem.
Yeah. Okay. Well, I've got as much bandwidth as I've got. I don't know what else I can do at this point. I'm going to carry on. If it's still, are you not able to hear me, or is it the video that's not stable?
No, we see the video, but the voice is a bit broken. So when it's a bit detached. So we don't have a perfect flow of the voice.
Yeah. Okay, so I've got two options here. I can continue for a bit, or if you've got another presentation you can follow up, I can go and get a better internet connection. I'm not far from my...
You mean, so I don't know how much time you need?
I can be, my labs are only about 20 minutes away, so I could actually go there and do it from there. I'll have a better connection.
20 minutes. So what time is it?
Well, do you have a presentation following this that maybe you could do first?
Maybe, I don't. So if we can. Okay, let's do it. If it's not so too much an inconvenience for you.
No, it's okay. It's fine. I'm sorry. I'm trying to do this from home, but I think my connection is just not good enough for it. I'm gonna head in. I'll head into my lab, and I'll reconnect. Okay.
Okay. So
I'm very sorry. I'm very sorry about
this.
this.
Not too much. So thank you for your.
No problem at all. Okay, guys. I'll catch you shortly.
Okay. See you later.
All right. Thanks. Then. Bye bye.
And so a double thanks for. So it seems we have time for several questions. But I think that we may proceed with the presentation while if you were able to hear, Ray Green, Professor Green from the University College in London is actually moving to the lab. He was trying to connect from his home, but it seems, or his personal office, but it seems that it didn't work, so he's moving to his lab where he has more bandwidth, because typically the problem is bandwidth. So I pretend that this platform will one day allow to teach or to attend the classes from the beach, but we still need an improvement in the available bandwidth, even in London, I mean. We had planned for later a presentation on brain on the vat from AGH in Krakow. Maybe they want to give it in the next minutes. We may have a short break, but we may use the break for testing with Krakow, if they are still there. I think that you are on the. I think that you are on the right path, but you still have to do something.
Okay.
Okay, now I see the presentation.
Mm-hmm.
I think I still don't see your video, but
Okay, can you constantly hear what I'm saying right now?
we have difficulty.
Okay, shall I say something in not so loud, or what? What's the problem?
Well, it
Camera?
seems the same problem that we have with Ruari before.
Oh, I see. Okay, so shall I just...
I think that you should silence your, not your microphone, but your speaker, because I think there is an echo.
Okay, can you hear me now?
Now it seems better. Now it's better.
So shall I start the presentation on HGH University and then move to brain in vet problem?
Yes.
All right. So
Okay.
So hello to everybody. My name is Chris Pomorski, and I am co-organizer of Shanghai Artificial Intelligence Lectures in Krakow in Poland. Today I would like to give a short description of AGH. So basically it's the first biggest technical university in Poland. We are located in Krakow. Poland is a country between Germany and Russia, and also we have Czech neighbors. So basically Krakow is a city with very long traditions, and Jagiellonian University was founded before University of Cambridge, and AGH University was created just after First World War. It's a pretty big university. It has about 30,000 students and about 1,000 PhD students. It has 167 full professors, 260 associate professors, many assistant professors, like more than 1,000, and many assistants, like 400. So, and this university is deeply interconnected with industry, and also there is some development of robotics, and so basically there are 15 faculties at AGH. So it originally starts from Faculty of Mining and Geoengineering, Faculty of Metals Engineering, Electrical Engineering, Mechanical Engineering, Geology, Mining Surveying, Materials Science, Foundry Engineering, Non-ferrous Materials, Drilling, Oil and Gas, Management, Fuels and Energy, Physics, Applied Mathematics, Humanities, and also right now these lectures are transmitted to Faculty of Computer Science, Electronics and Telecommunications, and this is the big lecture hall which was dedicated to this lecture. Okay, so now I would like to move to the presentation of students. So we have a brain in a vet presentation. So this is a philosophical presentation, and well, let me introduce the student. Yes, please introduce yourself.
Okay, thank you. Thank you.
Okay.
I love Krakow. It's my favorite city.
Yes, you are invited to come, whenever you like.
Okay, thank you. It's really a very nice old city. Typically, kind of nice city that you find around, in particular in Europe. Sorry, no, in many kind of places. No, it's one of the most beautiful cities in the world, I think.
Thank you.
Okay, fine. So my name is Carolina, and I would like to describe a philosophical problem called brain in a vat. And functional principle of brain in a vat is that we took brain off body, connected with a supercomputer, and sent electrical impulse to create a simulation of a real world. And what it's all about? So the most important thing is the brain. This is the most complex organ in our body, and it probably conditioned the existence of self-consciousness. And consciousness is a fundamental mental state. Entity is aware of external, like I think, therefore I am, and internal phenomenon. And maybe let's imagine a brain in a vat. And then the most important question is how to state what is real. Well, this question is really hard. Generations of philosophers failed because even in ancient Greece, philosophers started to ask themselves, what is real? For example, Plato thought that we are locked in a cave and what we see on a wall is just a reflection of the real world. So our reality is just a reflection. Then Descartes, in the Meditation on First Philosophy, thought that nothing is real. Devil sent us images of reality, and false is all around us. And then Kant's point of view is it is really important to know what's true, it is provable, it's really knowable. So let's have a look maybe on a PUTTMAN'S idea. And we can see that his ideas are built on a paradox, because if we assume we are brains in a vat, then brain does not refer to a brain, and that does not refer to a vat. And if brain in a vat does not refer to brain in a vat, then we are brains in a vat. The sentence is false. So if we are brain in a vat, then the sentence we are brain in a vat is false. Okay, so PUTTMAN asks how one thing can embody the other if similarity is not enough and not necessary. We need an intention, because word tree and our image of a tree is not a real presentation of the tree. So causal constraint is a term refers to an object only if there is an appropriate causal connection between that term and the object. Okay, that's complicated because so as you can see, in a sentence, we are brains in a vat, nothing is true. Any word or concept represented by this word does not have a correspondent in the reality. Brain isn't corresponding with brain, etc. It's getting complicated because any statement about brain in a vat isn't relating to the brain in a vat. It can't relate to anything else, but certainly not to the brain in a vat, more specifically to a state of being the brain in a vat. So even more, if we are brains in a vat, that's as plain as day that statement we are brain in a vat is true only if we are brain in a vat. And as we see, CC is very important to arrive perception. But PUTTMAN'S mind experiment evident that brain stuck of body experience the illusion, so it's not a real world. PUTTMAN wants to prove that we can't imagine that we are brains in a vat. This statement refutes itself. If we consider it is true or false, it must be false. And BRUECKNER made it even clearer by introducing self-awareness into a puzzle, as you can see. And what is true? Definition of the truth made by Aristotle is to say of what is that it is not, or what is not that it is false, while to say of what is that it is. and of what is not is true. That's pretty complicated, but if you think about sentence, grass is green, it's true only and only if grass is really green. That's simple. And, well, that's the Wright's version of brain in a vat. And he's proved on a base that even language is important. But by nature, we can't speak same language. So we can't be brains in a vat. And it is really provable. Well, some philosophers have claimed that even if PUTTMAN'S argument is sound, it doesn't do much dislodge Cartesian and global skepticism, because Cartesian thought that I think, therefore I am. Crispin Wright argues that the argument does not affect certain versions of the Cartesian nightmare, such as my brain being taken out of my school last night and hooked up to a computer. Then it said in 1991 that it's physically impossible for a brain in a vat to replicate the qualitative phenomenology of a non-invented human being. Well, it's still not possible today, but look at some science fiction movies like Matrix. So that's all, and I invite you to study philosophy because it's pretty interesting, and see you.
Okay, thank you. Thank you. Actually, this brain in the vat paradox is a very, very stimulating one, very interesting one. Actually, I think that the issue is that, so if it is really possible to build a perfect simulation replica of the real world, that might not, I mean, that should include a simulation of a body to work. So I think it's a nice. So I'm not as sure as you are that it's in principle it's possible to build a matrix. Actually, because the real universe of matrix includes what is perceived by the people in the matrix plus what's outside of the matrix. But no, I think it's an interesting issue. By the way, this is a challenge from people from Asia, because as there are nice cities in Asia, there are also has been a very rich philosophical tradition actually approaching this problem. The problem, which is the problem that you have for the fact that they are a human. So what is real? Because that's the real point. What's real? Because we all know. So I mean, there is really a lot, both in literature and philosophy. There is a lot of consideration about this in all the major culture of this planet, of course. So if it would be a very nice challenge if someone from China or Japan wants to put the same issue in a local perspective. We are now actually part of all of the same big culture, but maybe if you have been grown up in an area, you understand better the tradition of that area. So I know something, but maybe you guys can tell me more. You lost? So I know that from Xian, by the way. So if any students wanted to discuss with Carolina, I think they can send an email to me, for example, and we can forward to her, and maybe we may even have a students panel next time or in the future. So thank you. While we wait for Wairi, who is still not connected, I think that Xian might present the site and do a student presentation. Oh, yeah.
Different points or different comments and suggestions or the personal point of view, okay, and some questions.
Dustin.
Okay.
Okay, when you want to do your presentation, we are ready.
Maybe next week, okay?
Okay.
Okay.
No, if you prefer, because we are still waiting for Wairi, but if you prefer, next week is okay for me.
Okay, I will inform you, okay?
Okay, next week.
Next week, okay?
As you prefer.
Okay.
Next week.
Thank you.
Okay. Now we have Wairi, so because I know that for you and the Japanese, it's becoming a bit late now.
No.
Hi, Wairi.
Hi, guys.
Much better.
Good.
Also, the video is much better. So
great. Okay.
And really thank for the support that you did, because
it's no problem at all. No, really, I'm just sorry about the delay for those of you who are towards the end of your day.
It's okay.
Let's
but
see.
It will be worth the wait, so it's okay.
I hope so. Okay.
I don't want to put too much pressure on you, but.
So, can you see video footage now? Is that all right?
Yes, perfect. Yeah, much better. No, it was bandwidth. Bandwidth is very bottleneck.
Yeah. Okay. Good. All right.
Okay.
So I'll just continue from where I was, which was just showing you some examples of where robotics have been part of processes for making buildings. And this is some of the kind of research that we do, but it's not what I wanted to talk about today. I'm going to talk about more of my artistic perspective on robotics, particularly in the way they make people feel and in sort of how I came to robotics. But this is just some of the results of working on this building in London. So I want to talk about this, for example, as a photograph from a piece of work that I did in the Tate Modern in London. It's a large underground space, a gallery in central London, that's where I was using robotics to kind of manipulate a light source that's moved around above the public's head. I'll show you a bit more about that in a bit. But the other thing that I do is I direct the Interactive Architecture Lab, which is in UCL, and we are a master's program. It's called Design for Performance and Interaction. It's a master's program that's very multidisciplinary, and we bring people from all sorts of backgrounds. So we build robotics, but we work with performers, we build interactive environments. This is an example of a project where, actually I'll show some of the projects later. This is just some footage from the process that the students are going through, which is kind of sculptural, but also using code, using mechanical engineering principles. So it's very much a kind of very multidisciplinary program. It involves a lot of, actually I'll just move on to the next slide. My background is an interaction designer, and I'd come to interaction design through, and really through, well, I came to study architecture, but I was always interested in interaction design. And so robotics became a very important thing for me in trying to think about how the world of interaction design left the screen and started to become part of the physical world. And I also was very interested in breaking the traditional interaction models that you find in screen-based interaction design, and the idea that really we're just using technology to sort of do things. So it's this master-slave kind of notion of interaction, which is kind of has its roots in very early ideas about what computers are there for, which relates maybe to the earlier comments, Fabio, about slaves, about the use of technology for slavery, sort of modern slavery. I think that's there's lots of good uses for that, but I'm kind of interested in some of the more psychological and social aspects of it, and personally, and or I find those more aesthetically interesting. But I certainly see a lot of opportunities for using robotics also to do very menial tasks that we may not want to. When I was trying to explore models of interaction that I would be more interested in, I found this photograph of two fencers, and I like it because it's basically a single exposure photograph with two flashes. So you see the beginning and the end of these movements, and there's a line drawn in, with light that shows the path that the foils that the fencers are using goes through. And there are moments right at the top, if you look at the top middle of the image, there's this kind of wobble or a couple of changes of trajectory, and I see those as being perhaps moments of interaction, where there are kind of multiple participants who are acting into the world, reacting at the same time, and adapting their behavior as they go. So it's much more about dialogue, a physical dialogue, than it is about, say, controlling one controlling another. The ideas about having an architecture that might have a dialogue with us, or might have not just a sort of master-slave relationship, but might actually enter into a kind of conversation with us, began actually in the 1960s. This is a work by an architect called Cedric Price, who imagined the future of architecture being made up of a huge kind of shipping container shipyards, which would reconfigure and build architecture continually, so that you could have so that the building would always be different each time you entered into it. The results of this project actually were never built, but you can see some examples of modern buildings that have taken on these ideas. Probably the most famous being the Centre Pompidou in Paris, which is quite a reconfigurable building. All of the services for that building are on the outside. The reason I showed this to you today and share this perhaps with you guys, because you may not be familiar with some of this work, is that there was a cybernetician who also was part of this project called Gordon Pask. And he proposed the idea that the building would, if it got bored of how people were using it, that it might reconfigure itself and propose new types of architecture. And I thought that this is a kind of interesting proposition at the time, and I'm kind of interested in how this can come about, perhaps it's someday in the near future, not necessarily in this kind of rigid, mechanical sort of infrastructure that you see here, but in some other kinds of new forms. I'm also really fascinated by work like Hod Lipson and so on. You guys will all be familiar with some of this work. This is work that I saw when I was actually a student, so it was just, I wanted to share some of the things that had kind of made me think about how I might be able to design environments or art projects that actually would adapt their behavior over time. And the results of that was, of my first entry into robotics, was these four creatures that were called, the piece is called Performative Ecologies. These are four machines that essentially are born into the world without any idea about their own physiology, but but they have this instinct to turn towards people and to create performances with these simple tails, these LED lit tails. And they perform these little performances, and they measure the success of each performance. And so the fitness function, the genetic algorithm, and the fitness function being facial recognition allows us to be able to get these little machines to develop these really primitive performances over time. The idea is that each of them individually competes for attention, but then also when people leave the environment, they might turn to each other and actually start to perform to each other what they've learned. And so these machines are competitive but also collaborative within a kind of ecosystem of these machines. And this is my entry into exploring how machines might develop their own sort of aesthetic strategies, even though still quite primitive. When I showed this work in Brazil in 2008, in a gallery, there was about 250,000 people who visited this gallery over the course of a 4-month exhibition. There's enormous numbers of people actually getting to see this, and so there was kind of a large state training period there. And I had the quite unique experience of being able to come back to see my art project, but it had completely evolved its behavior over that time, so that each of them had their own kind of characteristics. But probably more interesting for me, though, was in the end was that many of the people who were working in that gallery would come up to me at the end of the exhibition and tell me about the 4 robots and be able to talk with quite a lot of detail about the individual characteristics of each of the 4 robots. And the people who actually worked in the room looking after the machines, looking after the public who were visiting them, had actually named all 4 of the robots as well. And so people have this natural tendency to anthropomorphize, to give life to these things, but also then to be able to sort of develop quite complex narratives about their personalities, their intelligence, when in reality these machines were quite primitive. And so I became interested in this and focused a lot of my more recent work. Well, this is about 7 or 8 years ago, actually. Sorry, not that recent. But this is working with puppeteers. This is Ronnie Ledrew, who I'd be showing him bits of robotics, and he'd be showing me his marionettes. And so we've been having a kind of ongoing conversation about how those things relate to each other. I've also been looking, of course, at the work of Hyder and Simmel. I don't know how many of you are familiar with this. Maybe this is very familiar now to anybody working particularly in social robotics. Here, this is a very early demonstrator. I think it's 1944, showing how very primitive geometry can actually can take on life and take on kind of narrative and qualities, and how we can infer or recognize emotion and agency with quite some sophistication from the movement of very simple bits of geometry. And this tells us something about the social brain and about the kind of perceptual cues that we use to work to recognize the world around us. These are just other experiments, and there's many of these that you can find. These are these kinds of, they look like sort of snowflakes blowing in the wind, but as soon as you put those darts pointing at the green dot, suddenly this thing feels much more predatorial. This now looks like a pack. This is called the wolf pack effect. And these now look like they're trying to kind of collectively capture the green dot. Although in fact, the movement of these is identical to the previous animation. It's just now that the darts are pointing at the green dot. So the way that our brain measures or recognizes agency has a lot to do with the orientation of objects. So this is a piece of work that I produced in the Centre Pompidou in Paris. This is a large kinetic double delta robot. It's a delta robot lifting up and then suspending a second delta robot underneath it. This is a response to the gallery it was inside of. This is the Picasso gallery. And this is a machine that basically mirrors the behavior of the people who come up to it. So I got rid of all of the learning algorithms, and here in this context, actually, it simply copies or reflects back your behavior on you. And this is a principle that's somewhat sort of derived from looking at things like mirror neurons and how we build empathy by mimicking each other. And so I was trying to, this is a nice example of it here, where you see how as this person slowly creeps forward, it creeps forward towards them. And so this is a kind of, and this creates a very immediate sense of intimacy. It's quite interesting. So I got invited then to do an exhibition at the Tate Modern, which I mentioned earlier. And I wanted to bring this triangle, again, a little bit further forward, now looking at how it might float in a dark space. And so the robotics would become invisible, and the only thing that people would see is this light. So this is the head of that robot. It's a tetrahedron. The material that wraps it is called electroluminescent sheet. It's a perfectly flat white light. It creates a really mesmerizing kind of, almost hides the volumetric nature of the triangle. It's quite magical. And so I had to suspend that on a motorized rail. This is a 21-meter motorized rail. And then there's a 4-meter tall Delta robot built to be hung off it. The left-hand side is just the testing Delta robot. The right-hand side is the full-scale Delta robot with the head at the bottom of it, as you can see. And then here it is suspended in the gallery. You can see this is a huge space that it's inside of. So when people, and again, I wanted to use this mirroring technique, so there's no sophisticated computation here. Really, there's a very few lines of code. If you stand underneath it motionless, it kind of hovers above you motionless, just sort of waiting almost for you to do something. As soon as you start to come to life, it mirrors and responds to you, and so children, of course, were very active and would activate it and create these kinds of gestural exchanges. And then occasionally there were these triggered behaviors. So there's some very nice research into fundamental behaviors that we recognize through motion cues. So this would be an example of it evading or escaping. And this is an example of it playing. There's research in artificial life research that actually sort of recognizes some of these kind of fundamental motion characteristics that you can use to recognize certain behaviors without having to be explained to you. I'm not sure if you're going to be able to hear this sound, but let me, Fabio, the only thing I can see is your face. So if you can't hear the sound, would you just nod, let me know?
It reminded me of being in one of those scary films.
It reminded me of one of those dreams you have, when aliens sort of invade the Earth. And it seems something like that. The triangle light came on and appeared to be following people.
It kind of creeped me out how it knew how people were standing and where to go.
You could see the reactions of all the other people. They weren't quite sure what was going on.
You expect something a bit scary, but then, I don't know, its movements are kind of organic, and I don't know, it seems very friendly.
Okay, so that last comment probably is one of my favorite ones, and it connects with this nice image here where you see a parent lifting their child up to reach out to try and make contact. Now, for me, that's a sort of sign of success there, that there's this what need to reach out and have intimacy. It's actually a very foolish thing to do, to lift your child up into the path of a moving robot like that. But anyway, nobody got harmed in the making of this video. This is some more recent work in Sao Paulo. I built it for a smaller exhibition using a universal robot arm. It's a much smaller range of motion, but able to get a little bit closer as well because of that. So I wanted to sort of spend the second half of this talk just showing you some examples of the things that are perhaps a little bit non-standard for robotics research, and just to recognize right at the beginning that machines is actually something that's been part of architectural practice for a very, very long time. And so in many respects, the architects were the earliest machine makers, and the oldest surviving piece of literature in architecture contains an entire book dedicated to machines. This is Vitruvius's Treatise on Architecture, and the final book at the back is the most fun because it's full of all sorts of strange, wonderful contraptions. So I highly recommend you take a look at it, and I think it connects the worlds of robotics and architecture after many centuries of being apart from each other. Now. This is just some footage of my practice in working in our studios, working with our robot arms, but also building custom robots. So we have our manual and our computer controlled lathes and mills, and we actually build and develop our own hardware. This is a very finely balanced needle-like robotic arm that we built, for example, to be suspended inside of a custom-built sculpture. This is in central London. Excuse me. This is in central London. This is a copper ring structure that was suspended around the robot arm, and the rings will have text cut out of them, and so as light travels around inside of the sculpture, projecting light through the text onto the surrounding architecture. So this is kind of seance. This building, being an abandoned church, has a certain kind of quality to it as well. So this is an example of the architecture, kind of bringing robotics and art and architecture together. The context of a lot of the work that we're doing is in recognition that the entire city is becoming much more connected, and that we have to develop our architecture in relation to these new types of sensory and responsive technology, and to recognize the buildings are in some ways becoming increasingly robotic. And so part of what we do is teach people in an architecture school, we teach them how to code, how to build circuits, and how to do things that you guys will all be very familiar with. And we're also recognizing how things like, we're going to have these robot birds flying around our cities soon. We're going to obviously have these kinds of strange new kinds of animals walking around our cities. We're going to have all sorts of, robotic cars. These are all things that you'll be aware of, but we're thinking about how they relate to the, to how they change the built environment, sorry, I lost my train of thought. How they change the way that cities are, at the moment, a lot of the cities are roads, but actually with these cars, you'd be able to pedestrianize. With automatic cars, we'd be able to pedestrianize 3/4 of our city, because we would have a much more efficient transportation network. And we're also interested in the kinds of digital layers that might sit on top of the physical layers that we're inside of. So there's a range of different ways that we're thinking about technology, augmenting the kind of the built environment as it currently is. We're also, of course, interested in how these new types of new types of learning systems are going to change the way. This is, of course, the kind of massive increase in computational power that we've seen recently with recent research in machine learning, is how that's going to change how robots can actually recognize the world around us with greater and greater sophistication. And so with that higher resolution of data, to be able to respond to us more directly, with more sensitivity, but also we're interested in how these technologies then start to build machines that can dream themselves, that can become creative and generate things that we haven't proposed to them. I'm also quite interested in how these robots might start daydreaming as they're walking around our shopping malls. But I'm interested in all these kinds of, these kinds of new sorts of creative and aesthetic opportunities. And the fascinating research that's going on right now with bringing robots back into kindergartens and using these much more behavioral approaches to learning, and the kinds of qualities of the movement that come out of that are far less robotic and far more human-like, I suppose, much more animals. So all of this relates. I wanted to just finish by sharing with you that one of the things that I recognize is that, sorry, lots of distractions here at the moment. There's a big need, in my opinion, for design and arts to become part of how we approach robotics, and how we bring the world of technology and design together, and trying to find kind of creative approaches to doing that. So when I look at these technologies, I look at them as these kind of aesthetic possibilities, and we treat them with kind of a sense of naivety in some ways. Designers and artists, we don't fully understand the mechanisms behind them, but we're kind of compelled by their potential. And so what we do in the master's program is we introduce these technologies to designers. So we build new types of robotics. This is a little kind of robotic face that mirrors your facial expressions, but it uses magnets so it can manipulate ferrofluid that's held inside of a frame. That frame is then held on a wall and controlled from behind a wall. So now you've got you've got a robot arm perhaps behind a wall, magnetically manipulating a frame that lives on the other side of the wall. And in doing so, you're able to create these kinds of magical experiences where this frame, little bits of what would what would typically be a static part of the built environment can come to life. This frame has a little pinhole camera inside of it that can see people's faces and actually mirror and reflect some of their expressions back to them in an abstract way. We're obviously playing with soft robotics because it's beautiful and interesting and playing with the kind of possibilities of it. But if one of the things that I think we're doing a little bit differently is wondering about the kind of qualities of, translucency that might come through these and the qualities of color and so on. So really interested in the aesthetic possibilities of these things, perhaps exploring spaces that typical robotics may not have an interest in or may have missed, seeing how they might relate. Interestingly, though, there's architects who have been thinking about inflatable buildings for quite some time. So this is just a nice image from the 1970s of explorations of what a soft robotic building might look like. So I love the kind of imagination of architects in the mid-20th century who sort of seem to be prophesizing some of these. There's quite a few of these. I don't want to show you everything. I want to just show you a few of my favorites. This is just some of the students' work. These are explorations with fluidics. But we were looking at how you might be able to build a mobile soft robotic pump system. This has a 3D scanner on the front of it, so this is a wearable. It scans the environment and then essentially is able to build a three-dimensional model. So you can blindfold somebody, put them in a space, and as they move around, these soft robots inflate and deflate around their skin to give them a sense of that space. So possible applications might be people where there's limited vision, like people with disabilities in vision, or limited sight situations like firemen and so on. So these are sorts of, we're exploring these for their design possibilities, but we're also exploring their kind of the new aesthetics of this and kind of the futures that these might lead to, the kinds of new types of wearables that might exist because of these. This is a robot that I'm quite proud of. This is with the work with the students. This is a garden that plants have not got a nervous system, but they can be electrophysically measured, physiologically measured. And so we were able to measure those plants' states and use those to actually control a robotic rig. That rig is housed within a geodesic sphere that allows the structure to be able to roll. So essentially, as these gardens push out, they change the center of gravity of this structure, which allows the entire geodesic sphere to roll. And so the plants that are on board this rig are able to kind of democratically vote on the orientation of this garden. And we kind of proposed the idea that this might allow these plants to be able to become mobile and travel around the city looking for microclimates to be able to repopulate. I'll skip the work with neural nets, I think. But I'll show you this. This is work with one of our students who was a dancer and an architect. And we were showing her, we introduced her to these body tracking technologies, so she was able to take these movements to be able to rationalize those into simple geometric forms, just as you do in dance notation. And then she was able to hand these aluminium rods to a pipe bender and a robotic arm that would bend these elements and then hand them to her. And she would then place these into the space. And so as she performs into the space, the robot continually builds these little bits of notation describing her performance. And so over time, as she moves, the architecture kind of gets built up. And so at the end of this dance between her and this robot, you get this artifact as a result of that. And this goes on. And so just to finish on this, this is what we are doing with our students at the moment. We've just started our program here. Whoa, really bad music. This is our puppeteer, Stephen Mottram, who we just had here with our students, teaching basic puppetry techniques to the students. So bringing this into the conversation about when you're designing things that move, just really appreciating fundamentally how the brain processes these things. And so we kind of bring these conversations into the classroom right at the beginning of the year to sort of generate lots of ideas and to think about how sensitive the eye is to movement. This is just lots of little things done. So I just wanted to sort of finish on saying that you know, I think it's really important that designers work with robotics, but also that our designers and artists and architects are part of the conversation about what we use these things for and how they, you know, and become part of the design of these projects. So I think we need to have more collaboration between the arts and the sciences on this subject. But I also think, you know, one of the ways to do that is to encourage designers to go out and study art robotics, which is what we try and do in our own humble way. But I would also say, you know, if there are any of you guys out there, any students who are interested in studying design in the context of robotics, we have, you know, we'd welcome you to come and join us at UCL. We have roboticists actually in the studio this year who are part of the project, and I think they're enjoying the fact that they're in a very different environment, thinking about where all of these new technologies are taking us and taking society. So I think that's it. Thank you very much for your attention.
Okay, thank you so much. So finally, we succeeded and we could listen to your great talk. We are a bit late, so but if there are questions, we will be happy to. I think well, we will be very happy to answer. So let's wait. So please use the chat to show your intentions.
See the chat.
So I don't know. So it seems that we have no questions.
I understand.
No, personally, I have a comment, but it's really very interesting. And I really share your idea that robotics needs design and the opposite. So, no, you are right. No, actually, one of the comments that we modern people do on the Greeks, ancient Greeks, what we used a lot of technology for entertainment. But on the other hand, this is also a very nice lesson. I mean, you're right. Xectibius or Aaron of Alexandria were actually using machinery for architecture. Yeah. So
yeah, and I think if you look at
you are not as original as I thought initially.
Yeah, no, I agree. Yeah, I acknowledge that. It's true. Actually, some of my greatest heroes of, you know, there's Jacques Van Cansen, who's the guy who did the famous duck, but he actually also invented a number of machine tools and a lot of very useful things along the way. Often the motivation was to create kind of spectacular experiences, but often the actual need to be able to reach those kind of possibilities, many great inventions had to come about. And so in a sense, sort of the history of robotics is very much driven by the desire to make performative machines much more than it was to develop, I think, functional, you know, construction machines, for example.
No, actually, I fully agree with you.
Yeah.
So you are reviving an old tradition, so to speak.
I am. Exactly.
And you are doing it in a very attractive and inspiring way. So thank you so much. Thank you so much. And so let's keep in touch. So since I think that people is a bit tired, so I think that Ruairi will be happy to answer to any question. And this is in particular for students. They are welcoming people in their lab. So
yeah, I'll just give you my on the chat. I'll give you guys my you know, my contact details, so you guys can just you know, you guys can just contact me directly if you want, if you've got any questions later. Anybody's too shy right now to do it. I understand.
It's also late, because we were supposed to finish half an hour ago. So, but anyway, so feel free to thank you everybody for attending. Thank you the speakers for giving a very interesting talk. And so see you next time. See you next week. Thank you. Bye everybody. Bye bye. Bye bye. Traditional